Okay, so today we're going to do the layout of an op-amp, and yeah, we have our test bench for our op-amp here. At some point we are happy with all the simulation results for our circuit, and it is time to move to the physical implementation and physical verification. And before that, I'm going to show you what we're going to lay out. So we have our op-amp here internally. It is a simple two-stage op-amp. The input of this op-amp, we have a positive input, negative input to a differential pair. The differential pair has a active load, current mirror load here. The second stage is just a common source amplifier. We have a bias input of 1 microamp, and this current it is mirrored to the tail current of the differential pair. Is a cascade current mirror, so we are going to lay out a cascade current mirror here. And the input current is also mirrored to the output of the output stage. Is biasing with 15 microamp. So the differential tail it is 2 microamp. So first you notice here that I have annotated the currents. I use the note here, text or shape, to annotate the currents that I am using, and this is useful information because we have to dimension the tracks for the current that they have to stand in order to avoid the electromigration. So I used to put the value of these currents in each branch of the circuit, and then I also mark the devices that have to be very well matched, because most of the effort during layout will be to get the matching of these components. So first and the most important is the input differential pair. This has to be very well matched. So it is a differential pair here. We have the PMOS current mirror that is working as an active load here. Has to be also matched. It's a current mirror, and then we have the current mirror here down. Also, when we need to match components, what we do is that we take some unit value. In this particular case, we have this transistor that it is length 2 micrometer with a width of 10 micrometer, and then I use the multiplier. I don't use the finger, I use the multiplier. So it's a single finger transistor with a multiplier of 2. So this transistor has a total width of 20 micrometers, so it is 2 times 10 micrometer. Then the transistor M2 is the same base transistor, same unity transistor, multiplied by 4. 4 times is 4 times, so it carries 2 microamps. And then the last transistor is the same unit transistor multiplied by 30 times. So we are going to be laying out a rather large current mirror with these 3 devices. For the differential pair, we have the transistor has a multiplier by 10. We are going to discuss the advantage or disadvantages of having even or odd number of transistors in the mirrors or in the differential pairs. And for the PMOS, we have the multiplier is 8 for each transistor. For the cascodes don't need to be matched. So instead of multiplier, I am using fingers. So this is a single transistor with 8 fingers and a single transistor with 16 fingers. So the devices don't need to be matched. The output transistor also, it doesn't need to be matched to anything. Okay, and we'll talk about this a little bit later, so we can delete it. Okay, so after this, we have a resistor and capacitor for compensation. So we are using this Miller compensation technique. Okay, some simulation results. Let's see here. I'm going to simulate DC operating point transient pole 0 and the AC simulation. So we run the final test before we move to the layout of the op-amp. So now this op-amp, it is connected as a buffer. You can see it is just negative feedback connection output with a negative input, so it works as a buffer, and it is driving a 5 pico Faraday load. So run the simulation, and then we check. Let's take a look very quick. The positions of poles and zeros, and we can put the zeros in the same figure. Okay, so we have three poles, and that they are located close to the Butterworth position. So you can see that the circuit it is quite stable. We don't need the input here, and we can plot this in logarithmic scale. So it is well behaved in frequency also, with a bandwidth of around 10 megahertz. Okay, so this is the circuit that we are going to lay out.